So here we talk about the slides, the label conjecture, and the cable of the figure in time.
Thank you very much. It's always very nice to visit Kai's. I'm not sure why I'm here because everyone else is doing this projective geometry and three manifolds, and here I'll be talking about four manifolds, which is very weird, but yeah, I hope you considered it enjoyable. Yeah, yeah. Okay, so the so first of all, to start with, the title says everything. So today I'll be talking about, well, why is this not working? Okay. So we'll be talking about this figures of the cables of the figure eight knot, in particular, even comma one cables. Well, the most historically correct one will be the question. The most correct question will be the to consider the two comma one cables of figure eight knot. And this question was asked first by Kawauchi in eh, uh, yeah, okay, whatever. Yeah. Yeah, so yeah, what are I talking about? Yeah, Kawauchi asked in one of his very old, unpublished manuscript written in 1980 about whether there's some 2,1 cable to figure eight knot is smoothly sliced. So what is this 2,1 cable to figure eight knot? Here's what it is. This is something called the figure eight knot, which is the only knot which is amphichiral in crossing number four. And this operation is called it taking the cabling pattern. So this is called a cabling operation. We have two strands, and here you have a one half twist. That's why it's called 2,1 cabling. And anyway, the question is whether this is smoothly sliced. What does it mean? And why is this question important anyway? So this question is important because this is directly related to one of the attempts towards disproving something called the slice ribbon conjecture. So recall that a knot is just a smooth, in this talk, just a smooth embedding of a circle in S3, and we say that two knots are equivalent if they're isotopic, ambient isotopic in S3, and the unknot, so if you consider whether the knot bounds a disk inside S3, that uniquely characterizes the unknot, right? If it bounds a disk, then it's an unknot, and unknot bounds a disk. And now what we want to do is we consider the same question, but not in S3, but by considering three sphere as a smooth boundary of the standard four ball. In this setting, we can consider the similar definitions, but using this but where you require that disk to be not embedded in S3, but smoothly embedded in the four ball. That gives you the definition of smooth concordances and sliceness. So to actually spell it out, we say that two knots are smoothly concordant if they co-bound a smoothly embedded cylinder, so they bound an annulus. And we say that a knot is smoothly sliced if it's concordant to the unknot. And it's equivalent to saying that bounds a properly embedded smooth disk inside the four ball. And determining which knots are sliced is a very hard question in general. If you there are very many like numerical obstructions to saying that some knot is not sliced, but in general, if somebody comes to you and asks you whether the random knot is sliced at a gunpoint, probably you're not going to survive. But however, so this question is really hard, partially because it's revolving around this smooth form manifold topology, which is exceptionally bad. But however, there seems to be a three-dimensional condition which ensures this smooth sliceness of the given knot. So we say that a slice disk is a ribbon disk if it's induced by an immersed disk inside the three sphere, which only has something called the ribbon singularity. So if you look at this figure, this is an immersed disk, and only singularities here and here, where you have this strip like transversely crossing your disk on another portion of the disk. This is called the ribbon singularity. And if you have such a disk, then you can perturb this part to the fourth dimension to ensure that this not actually bounces smoothly by this disk inside the four ball. And this is equivalent to saying that this disk admits a ambient handle decomposition without what is it the in the order, critical points of index two. Okay, so then we say that a knot is called ribbon if it bounds a ribbon disk. And and okay, so by this perturbation argument, we know that all ribbon knots are slice. The slice ribbon conjecture, asked by Ralph Fox in 1962, asked whether the converse is true. So every ribbon knot is slice, so you ask whether slice knots are ribbon. So, it seems very vague conjecture and probably is false, but it's still wide open, surprisingly. And the one confusing point here is that we're actually not asking whether all slice not disk or ribbon. Of course, not all slice disk or ribbon. It's very easy to construct a counterexample. Take a very complicated two knot and puncture it. It becomes a slice disk of an unknot, which is not ribbon. But instead, we're asking whether if you're not bounds any slice disk, whether it actually bounds another disk, which is ribbon. That's why this question is hard. So, and yeah, that's partially a reason why it's still very open. However, has been attempts to disprove this conjecture because many people think this is false. And of course, this by constructing potential counterexamples. And one of the most famous approach was given by Miyazaki in 1994. What he proved is that if you have a negative amphichiral fibered knot, so negative amphichiral means if you take a mirror image of your knot, it's isotopic to itself, but orientation reversed. And we assume further that its Alexander polynomial is irreducible. The most simplest example of a knot satisfying all these conditions is the figure eight knot. Under these conditions, then what he proved is that for any positive parameter n, if you take the two n comma one cable, so if you take the two n parallel strands, the cabled knot is never going to be ribbon. But on the other hand, there seems to be no reason why this knot should be sliced. So should not be sliced. So if you can find one of these examples where you can explicitly construct a slice disk, then you're now disproving this slice ribbon conjecture because it's guaranteed to be not ribbon. Okay, so to do this, let's look at the simplest possible case of this potential family of potential counterexample. It is a very wide family. The simplest one is for the figure eight knot, and the smallest positive integer is one. So we have reduced again to the Kawauchi's question. Is it whether the 2, 1 cable, the figure eight knot is slice? This has been open for 42 years since Kawauchi's manuscript. And this is mainly because all known invariants vanish, the computable ones. Well, the reason is that it's something called algebraically slice, and it's also rationally slice. So algebraically slice means almost all algebraic invariants vanish. Rationally slice means almost all known smooth invariants vanish. The S invariant from Kovanov homology also vanish. But in this talk, we will prove this, show you the very rough sketch of how our theorem was proven in 2022. So what we proved is that this is not slice. And furthermore, you can say a little bit more. What you can say is that it has infinite order in the smooth knot concordance group. What does it mean is that if you take the connected sum of several copies of this, then it's not going to be smoothly sliced. Okay. And this theorem can also be generalized in two possible ways. And of course, this is about whether you can change your knot figure eight to other and negative amphichiral knots, because Miyazaki's family is much more general than just this. So if you look at the quasi-alternating knots, then half of them, so by the Arf invariant. So if Arf invariant is a group homomorphism from defined in the knot concordance group, takes mod two values, so it's 0 or 1. So if it's non-zero, then it has infinite order. You can do the same thing. You can take the other family. So if your knot is no longer quasi-alternating, you can we cannot say something about this RF invariant, but you can define as something which is extremely similar to RF invariant is a conjecture where this is actually equal to the RF invariant. It was defined in another work of myself and Sean Park. And this is C Tor is the torsion subgroup of the smooth knot concordance group. For quasi-alternating knots, this equals RF invariant. So if you have any negative amphichiral knot, so this is a torsion, so that this is well defined, and satisfied that this value is 1, then you can still say that this 2, 1 cable is not smoothly sliced. So this covers all, like you can say that this covers half of all possible negative amphichiral knots, but it's just half. And you cannot say, we couldn't prove whether it always has infinite order, but at least we were able to prove that this is not sliced. Okay. And now Miyazaki's family also covers higher cables, 2n, 1, where n is bigger than 1. So for example, 4-1 cable, 6-1 cable, so on and so forth. In this case, in my joint work with John Park and Masaki Taniguchi this year, we were able to prove that if your parameter n is odd, then the 2n, 1 cable is actually not smoothly sliced. We weren't able to prove that it is infinite order. We also were not able to prove that like in very large generalities such as this, but at least for the figure 8 case, we were able to prove this thing. Okay, and its proof is completely different in the 2-1 cable case. So, and it will be the main topic in tomorrow's talk. So, and for today, we'll discuss only about how to prove that 2-1 cable is not smoothly sliced. Okay, so as always, proving that some knot is not sliced requires two things. One thing is to choose your own invariant, and the another part is to compute that invariant. Both are highly non-trivial. Here, so for this case, the obstruction comes from some extra structure in something called the Heeger-Floor theory. And of course, I'm not going to discuss what Heeger-Floor theory is, how it's defined, because it's a very complex thing. But I'll try to give a very, very rough sketch of what algebraically it is. So it's basically a three-manifold invariant. If you have a three-manifold Y together with a spin C structure, then the Heeger-Floor theory associates to this spin C three-manifold homotopy class of a chain complex, Cf minus of Y comma S. It is a finitely generated free chain complex of F2 of U modules, well-defined up-to-chain homotopy. It comes with a nasty grading, but it becomes much better when your spin C is torsion. Torsion means the C1, the first Chern class is torsion. In which case, the complex inherits a relatively Z-graded and absolutely Q-graded structure, and U becomes a variable of degree -2. Now, this chain complex is very special. The biggest property is that it has a very nice localization. If Y is a rational homology sphere, so that all spin C's are torsion, then for any spin CS, if you localize by formally inverting U, it becomes a ring of is homotopy equivalent to F2 of U comma U inverse. And this is essentially carrying out one of our constructions and arguments. Okay, so this was I said here Floor theory is a three-manifold invariant, but at the same time, it's also a four-manifold invariant in the sense that it admits cobordism maps. So, what the cobordism map is that if you have a spin C cobordism between spin C rational homology spheres, of course, they don't have to be rational homology spheres. It's defined in a much general context, but I'm trying to be very as simple as possible. So given such a data, so that this cobordism is from Y1 to Y2, then what you get is a chain map from between the Heeger-Floor chain complexes, and it's well defined up to homotopy. So its homotopy class is a spin C diffeomorphism type invariant of W comma S, so that we have this functoriality. So composition of cobordism map is cobordism map of compositions. And you can also compute the degree shift. And degree shift is some homological number. This is the formula, C1 squared minus 2 Euler characteristic minus 3 signature divided by 4. Of course, it can be rational because things are rationally graded. But yeah, this is the degree formula. Of course, this may be null homotopic. And this is almost always the case when B2 plus is positive. But when your cobordism is a negative definite cobordism, then your cobordism map is very nice. And so nice that if you take a localized U so that you get a chain map between localized eager flow homology, it always becomes a homotopy equivalence for every spin-C structure. And furthermore, if W is a rational homology cobordism, then you can directly prove them from this formula that your map is degree preserving. Okay, so that already gives you some rational homological Boltzmann invariant, which is called the invariant, but we're not going to use this right now because we need something more complicated. So I said we need some extra structure in Higler flow homology that comes from several symmetries. This one of them, we'll be exploring two symmetries. One of them comes from this topological symmetry. But the another one comes from the fact that the construction of the Higler flow homology has an intrinsic symmetry. It has intrinsically encoded Z2 symmetry inside this construction. We're not going to describe its definition here. It was defined first by Hendricks and Manolescu. It's called involutive Higler flow homology. So, but anyway, so the algebraic data you get is a degree preserving homotopy equivalence from CF minus to itself whenever from S to S conjugate for any spin-C structure. And this is well defined up to homotopy and is a homotopy involution. In particular, if your spin-C structure is self-conjugate, which is almost equivalent to saying that it's induced by a spin structure, in which case this can be seen as a homotopy involution from here to itself. And yeah, and note that they correspond actually. In our setting, it corresponds to spin structures. Okay, and we'll need another symmetry coming from topological one. So if you have an orientation preserving self-diffeomorphism of F on your three manifold, you can, thanks to work of naturality uh, due to Juat, Thurston, and Zemke, and also functoriality due to E and Zemke as well, we can define induced homotopy equivalence from induced by the self-diffeomorphism from CF minus to from spin-C structure S to F fullback of S. And this is again well-defined up to homotopy. And it is also functorial up to homotopy as well. And as in this iota setting, if your spin-C structure S is F invariant, then so that this and this are the same, then it becomes a homotopy autoequivalence. And this is especially the case when Y is a branch double cover of S3 along a knot, and so that it becomes a Z2 homology sphere, and therefore it has a unique self-conjugate spin-C structure. And if you take that, then since by the uniqueness, it'll be preserved by every diffeomorphism. And also, since it's spin-C structure, you can also use this as well. Okay. Now we consider how those symmetries are correlated with cobordism maps. So the setting here is that you have two rational homology spheres, Y1 and Y2. Actually, they don't need to be rational homology spheres. We just stick to the simplest possible setting. So, and let's take two spin-C structures, S1 on Y1, S2 on Y2. And let's say we have a spin-C cobordism between them, W, S. Then the cobordism map with respect to this spin-C structure will map CF minus of this to CF minus of this. And then you can ask whether this cobordism map is compatible with the symmetries, iota Y1 here and iota Y2 here. It turns out to be true. So it indeed forms a commutative square with respect to iota here and iota here up to homotopy due to a work of Zemke. And furthermore, you can do the same thing with the diffeomorphism and diffeomorphism maps. So if you have an orientation preserving self-diffeomorphism F, which fixes each of the two boundaries of W, then you can say the same thing. So cobordism map commutes with the diffeomorphism maps. This is a work with Zemke, and this is a work with Dye, Mallick, and Stoffregen, although proofs are almost identical. Okay, so given these facts in Higgs homology, now will roughly describe a obstructive strategy for proving the non-sliceness. Okay. The okay, so what is the obstruction here? So we're trying to prove that a knot does not bound a smooth disk inside a four-ball. To do this, suppose that it actually bounds a slice disk, then you can take a branch double cover of everything so that you get some rational Z2 homology sphere, sigma k, and some Z2 homology ball, sigma d. They're all smooth. And they have, since they're Z2 homology spheres and balls, they have unique spin structure. And for simplicity, we'll always denote this unique spin structure as SS. Okay, so by removing a small open ball in the interior of the sigma d, you can consider it as a cobordism between S3 and sigma of k. And this cobordism goes in both directions because, yeah, it's just a smooth manifold. So it induces a map between CF minus of S3 to CF minus of sigma k comma spin structure, and it also can be considered as a cobordism in opposite directions. So it will also induce a map from here to here as well. And therefore, we have this sigma d is a rational homology cobordism, so its cobordism map is degree preserving. The opposite thing as well. So if you write down the maps, cobordism maps from S3 to here and here to S3, they will both be degree preserving chain maps. And they will also commute with iota and tau actions up to homotopy, where tau is the deck transformation. And since they're rational homology cobordisms, if you localize by inverting U, it will become homotopy equivalences as well. So this information is the one that we will need to prove that the 2-1 cable of the figure 8 knot is not slice. But let's put all these things into algebraic framework so that we can deal with a bit more clean and better things. Okay, so algebraically, what things these Higgs floor theory looks like is that it looks like it's just a chain complex, which is what we call a HF type. And we say HF type just means that localization formula holds. And we say that this thing together with a homotopy autoequivalences of your chain complex is a iota comma tau complex if they are homotopy involutions and they homotopy commute with each other. Mod 2 field. The mod 2 field. Yeah, binary field. Yeah. Okay. And we say that a chain map is between the HF type complexes is local if localization gives you a homotopy equivalence. And we say a local map is either tau local if it homotopy commutes with iota and also tau as well. And we say that two iota tau local complexes are iota tau locally equivalent if there's this nice method in both directions. That forms a group very similar to non-concordance group. So you take the set of iota comma tau complexes modulo local equivalences. The group operation is given by the tensor product, where in the tensor product, the action is given in the diagonal. Then what is our sliceness obstruction here is that we have a map from not concordance group to this group by taking this CF minus of branch level cover at the unique spin structure together with the iota action and the deck transformation action. It's canonically a group homomorphism from the smooth concordance group. So if we can prove that this image is non-trivial, then we're proving that this given knot is not slice. But we're claiming a bit more, right? We're claiming that it's not just slice, but we're claiming it's an infinite order. So how to prove that something is an infinite order? We have to use the fact that this group, this local equivalence group, has a canonical partial ordering. The partial ordering is given by the existence of a local map in one direction. So if we have a map from C1 to C2, then we declare that this is not big, this is less than or equal to this. This is obviously invariant under addition, so this is invariant partial order. So, so if you can prove that some element in this partially ordered abelian group is less than equal to zero, but the converse doesn't hold, then we're proving that it's infinite order. So what we have to prove is that there's this local map from here to here. No, sorry. Here to here, but there's no local map from here to here. Yeah, that's exactly what we'll prove, which means that we have to compute everything. And indeed, the crucial part of this paper was that we can indeed compute everything. So yeah, this is a general strategy for proving that this is not slice. But this is just an abstract framework. It's built on the assumption that we can actually compute every chain complex and every action and every map, actually very non-trivial. In general, if your knot is just random knot, then it'll be just outright impossible. But in our case, we can take advantage of the fact that your knot is so special. Our knot is 2-1 cable of some knot. Some knot is figure eight. But in general, if you take the knot of the form something a 2-1 cable of something, let's say K0, then Montesino's trick tells you that if you take the branch double cover of this, then it is naturally diffeomorphic to the +1 surgery along K0 connect sum is reverse. And we also have to identify the deck transformation here. So we have a deck transformation action here. Then which action in here does it correspond to? It is given by strong inversion. So you're taking K0 connects on K0 reverse. You can draw in this way. So it obviously has a rotational symmetry. You can take a 180 degrees rotation, and it will flip the orientation of the knot, but it'll remain as a set. It'll be fixed. Such knots are called strongly invertible knots. And so what you can say is that this is has a canonical strong inversion, and if you have a strongly invertible knot, you can if you take any surgery, it has an inherited induced action, induced symmetry, and what is true is that the induced symmetry here corresponds exactly to the deck transformation here. Okay. For simplicity, assume that, well, here we're taking +1 surgery. But for Heeger floor setting, +1 surgery is usually very small, and small surgery is bad. Instead, for now, it is obviously a lie, but let's assume that we're working with +n surgery instead of +1 surgery. Yeah, and then we can reduce our problems to computing the induced action of the not fluor homology of this thing thanks to large surgery formula due to Oshrath and Szabo. What it basically tells you is that if your slope is very, very big, then this CF minus of surgery canonically corresponds to a certain subcomplex of CFK. Okay, not fluor homology is something that I didn't talk about up to now. Well, ideally, I should give you a formal definition, but it's obviously too much thing to do. So algebraically, what it is that given a knot K, it can be given in any three manifold is totally fine, but here we'll just say that your knot is an S3. Given such a knot, this knot fluor homology associates to it a chain homotopy class of CF, something called the CFK. It is complex of modules over F to U comma V. Now you have two variables. It is also bigraded. And this data governs Heeger floor homology of large surgery. And how does it work is that here this has a bigrading and then two variables, U and V. You forget the actions of U and V and only remember the action of U times V. Then this chain complex splits along its Alexander grading. The one with the summand corresponding to the Alexander grading 0 is called A0 phi. So yeah, so this is a subcomplex of Alexander grading 0 elements. And it be considered as a complex of F2U modules, where U correspond to U times V in knot flow homology. Then, by counting some homomorphic triangles, you can define a Lahr surgery, which turns out to be a chain isomorphism from the plus n surgery with respect to the zero spin state structure to a zero subcomplex. It's an isomorphism of degree precisely 1 minus n over 4, where whenever you have a large enough slope parameter plus n. Okay. And in Volta-Peeger flow homology, well, it's a CF minus together with an involution, but you can define a knot-flow version as well. So if you have a CFK, you can define a homotopy. The same strategy gives you a homotopy skew autoequivalence, iota k. We say skew because it intertwines U actions and V actions. So it's not really linear, but it's skew linear. And it's also defined up to skew homotopy. It's also not involution because due to its construction, if you square it, it becomes an action where you rotate your knot by one full rotation. It's non-trivial. Due to the formula of Ian Zemke says it's homotopy, up to homotopy is given by 1 plus phi psi, where phi and psi are base point actions. But well, anyway, it's not order 4. In general, it's not order 2. In general, it's order 4. And also, instead of deck transformation in this diffeomorphism, we identified with a strong inversion of this knot. So we'll need the action of the strong inversion on the CFK of a strongly invertible knots. It is also well defined up to homotopy. It's also a skew autoequivalence. And here it is actually a skew involution. And this doesn't really commute even up to homotopy. It's because this is orientation reversing, and iota k depends on the orientation. So it kind of anti-commutes. So tau iota is iota inverse tau, and iota is order 4, so I just wrote that. Okay, let's recall the Lahr surgery isomorphism from CF minus of Lahr surgery to A0. Here, on this side, A0 is a direct summand of CFK, and CFK is equipped with iota k and tau k. And here is equipped with the iota and tau symmetry. The natural question is whether this isomorphism up to homotopy intertwines those symmetries. The answer is yes. The action of iota k and tau k induce action of iota and tau here. Okay, so and that's actually a work of Ian Zemke for iota and Mallick and Stoffregen for tau, but honestly, they're just side products of a natural and functional reality of knot flow homology. Okay, so we were talking about plus n surgery. So under the false assumption that the branch double covering is diffeomorphic to plus n surgery of a k connects minus k connects k reverse, we were able to show that we can carry out all the computation just by taking the knot flow homology. But that's not the reality, right? Because it's actually plus one surgery, and the Lahr surgery doesn't work here, so we have to relate them somehow. And this is done by constructing a canonical negative definite cobordism from plus 1 to plus n. How it's done is as follows. So we're given a strongly invertible knot, which is secretly a figure 8 connects and figure 8 reverse. And we take a lot of its meridians and arrange them in a symmetric way. And on every meridian, you take minus one surgery. That gives you cobordism from plus 1 to plus n. You just contract everything. Contracting each of them increases the framing here by plus 1. So if you attach n minus 1 of them, it becomes plus 1 to plus n. It turns out to be negative definite, and it's also simply connected. What does it mean is that it also has a unique spin structure, and since this Kirby diagram is drawn in a symmetric way, what it means is that there's a smooth involution on this full manifold, which restrict to the involutions of plus 1 and plus n. Also, this is negative definite, and it's also spin. As I said, it carries a unique spin structure. We also denote as S, and by uniqueness is obviously fixed by the diffeomorphism. Okay, so what do you get is that there should be a cobordism map from here to here. So induced by this negative definite cobordism, it goes from plus n 1 to plus n with respect to the zero spin-C structure. By negative definiteness, this is local. And since the diffeomorphism extends and also there's a spin cobordism, we also have this commutativity that it commutes up to homotopy with I1 and tau. And furthermore, we can compute this using the degree shift formula for your flow homology cobordism map. It turns out to be n minus 1 over 4. This is very nice because the large surgery isomorphism is a homotopy equivalence of degree 1 minus n over 4. They will cancel each other, which means that if you take a composition of them, so you go from plus n 1 to plus n, and then you take the large surgery inverse to a0, then their degree shift will cancel each other. So it becomes a degree preserving map, which is local and homotopy commutes with iota and tau. Which means that as iota tau iota tau complexes, we have a iota tau local map from here to here, so that we have an inequality this with respect to this partial ordering in this local equivalence group. So to prove that R naught is not sliced, we just have to prove that this A0 complex has a iota comma tau invariant homology class in grading 0, but does not exist as such a class, but its dual should have such a class. So that there's no local map from here S3 to here, but there is a local map from here to here. That will give you our desired result. So how do you do this? It remains to compute this A0 complex and iota and tau. Well, A0 is just a direct summand of CFK. So first thing to do is to compute the CFK. But this is just a connected sum. So by the connected sum formula, this decomposes a tensor product of this CFK of K0 and CFK of K0 reverse. And in our case, K0 is the figure 8 knot. And the CFK of figure 8 knot is well known. It's very simple, and it's partially because figure 8 knot is thin. It is alternating. And how do we compute iota k and tau k? Well, the iota for figure 8 is uniquely determined up to homotopy by the property that iota square is 1 plus 5 psi. And for tau, on swapping involution tau, so there's a explicit formula for this due to Mallick and Stoffregen. And under this tensor product decomposition, this is the formula. So iota is just a diagonal action composed with some error term involving base point actions. This swapping symmetry is also exchanging this and this, also has an error term, phi and psi, but they are formal partial derivatives of the CFK full differential with respect to formal variables U and V. So they can all be computed explicitly. So let's carry this out. The K is a figure 8 knot here. We have to be a bit careful because figure 8 knot is reversible. So its reverse is the same isotopic to the original thing, but we have to treat them differently because the symmetry from identifying this and this reverse is not really the same as the identity from here to here. So let's write the complexes differently as follows. So for this one copy, we take this complex where the iota action is given by a to a plus x and x to x plus v. And here we have to take it a bit differently. In particular, we're reversing its orientation. So a becomes a plus x plus d and x is x plus d. Then we take the tensor product. It looks like that. You have several squares and you have a free sum end. And then you apply this formula to compute iota k and tau k on the connected sum. I'm not going to show this in full general in the full detail, but what we only have to do is to just see the homology of A0. So you only have to consider cycles in at degree zero. And in the degree zero, the homology of A0 is 5-dimensional over F2. It's generated by X tensor X tensor D tensor X, something, D tensor D. You can compute iron tau manually. It looks like that. And then it follows that there is this no homology class here, which is invariant and also generates the local homology. So that gives you one thing. It remains to construct a local map in the opposite direction from A0 to the trivial complex. And that's easy. What you do is that you collapse everything here to zero and you just leave this alone. And then this actually homotopy commutes to iron tau. So there's such a map. And therefore, it follows that the 2-1 cable of the figure knot is not sliced and infinite order. This proves the main theorem. Okay. So that was a proof for the 2,1 cable case. And note that this method cannot be used to show that it is topologically sliced. So what does topologically sliced mean? Uh, Recall that in the introduction, I said a knot is sliced if it bounds a smoothly embedded disk in the four-ball. You can replace this smoothness by local flatness, which only requires just a topology. And that's very, very different from smooth sliceness. And in general, there's much more topologically sliced knots than smoothly sliced knots. And yeah, it's actually also a very important question whether this is actually topologically sliced. It remains open. If you try to apply our argument in the topological category, the problem is that our obstruction depends on the fact that the deck transformation of the branch level cover cannot be extended smoothly to a self-diffeomorphism of any smooth contractible four manifold. But Friedman theorem says, and if you have a contractible four manifold, then every self-diffeomorphism of the boundary contact extends continuously to a homeomorphism of the interior. So we have no obstruction. So it remains open. We cannot actually say anything. So if anybody can solve whether this is topological slice, it will be great. If it's non-slice, it's awesome. If it's sliced, then it's also really, really great because it'll be a first example of a fibered knot which is topologically sliced but not smoothly sliced. And that's everything I have to say. Thank you.